Hi, everyone. This talk has a bit of a pun in the title, Hidden Gems. As you may know from the general description of the talk, GEM here stands for General Matrix Multiplication. And these gems are really hidden because I assume most of us who do machine learning spend a lot of time using canned solutions such as MKL by Intel or CUBLAS by NVIDIA. And I was just curious, what these guys actually do to make things performant, because sure, we can use these libraries, but at the end of the day, there are lots of benefits from understanding how to make any numerical algorithm performant, both on the CPU and the GPU. So I just dug into this a little bit and decided to share what I learned. I'm not going to spend any time on marketing or anything like that, but I wanted to say that we're hiring. We're looking for Scala developers, the standard Scala stack of Akka, Play Framework, Spark, etc. We are definitely looking for a lot of front-end people, security engineers, systems engineers, etc. And C++, although the C++ group is mostly in Dublin. But in San Francisco, everything else. OK, without further ado, let's focus on the content here. So I'm going to talk about optimization on the CPU quite a bit, from just a naive triple loop order n cubed implementation of a matrix multiplication all the way to cache-aware algorithms. And my main interest these days is GPU computing, and so I'm going to talk about GPU optimizations as well. The reason I'm putting more stuff in the slides that I'm not talking about is because I'm adding more detail for reference if you guys want to check out the slides later. So why bother? Again, we can just use MKL or CUBLAS or things of that sort. Well, I really do believe that even though matrix multiplication is a very simple algorithm, a lot of the learnings do translate into other problems. And to give you an example, I went to the GPU TechConf in San Jose in April, and NVIDIA just announced that they were adding a graph library for GPUs. But hey, before CUDA 8.0, there was no graph library by NVIDIA to do your graph processing. So yes, you may have had CUBLAS and cuFFT and cuDNN, etc. But if you were dealing with graph problems, you didn't have an analogous library. So there's always something on the frontier that may not be canned and provided. And so from that perspective, I think it's good to learn what one can do from scratch. And matrix multiplication itself is obviously extremely useful. From affine operations and deep neural networks to convolutions for convolutional neural networks, although you could do convolution more efficiently using a fast Fourier transform. You can use gems in matrix factorizations, and here's an example of using a gem in LU and Cholesky factorization, for example. So yeah, it's pretty common, obviously. I'm not going to go through the basics of matrix multiplication too much, but because I'm sure you remember that if you have an m by k matrix and a k by n matrix, the inner dimensions, the number of columns in A and the number of rows in B have to conform, and then you get an m by n matrix, and you take the mth row of A and the nth column of B, and you get the m comma n element in matrix C, right? So here are some specs of the machines I used. Mostly I did the computations on this laptop, actually, just a standard Core i7 CPU. And there's a basic NVIDIA GPU on this laptop, 384 CUDA cores, but this is, I think, the Kepler architecture, so that's not the newest architecture. But the final demo that I'm going to do at the very end is based on the NVIDIA Titan X, which is pretty much a state-of-the-art for single precision computing. Teslas would be good for double precision, but people are actually going into half precision right now and even 8-bit computing. So honestly, I don't care about precision anymore that much. Anyway, so here's the naive C example. just a triple loop. We iterate over index I, which is the number of the row index for A, matrix A, and J, which is the column index of matrix B, and K is that inner dimension that has to conform. So very simple, right? We just accumulate these values. Should be really trivial. And because it's C and we want to be performant, we're probably okay using void functions, which is really horrible if somebody is a functional programmer, for example. But hey, this is math. It just needs to be fast. Is it fast, though? It's not. This is actually quite slow. It's 1,200 milliseconds. I'm going to actually give you some comparisons because it's really hard to think about that as a value without actually a reference to other measures. So, well, just for comparisons in Java, that's going to be twice as slow. Obviously, the JVM gives you some overhead, but hey, 2x is not too bad considering that in Python, if it's pure Python, it's going to be 180 times slower. But, it's an interpreted language. It can be forgiven for that. That's why we have NumPy. And speaking of NumPy, we get 74 milliseconds. So why the heck did my code in C take 1,200, right? This is very disturbing. Because yes, most of the computation here is happening in C and not in Python, but still, that's kind of disturbing. And MATLAB and Octave gets us 20 milliseconds. So okay, 50x faster than this stupid triple loop solution. So what is going on? I can't really get into too much detail of modern CPU architecture because that's a whole separate topic for a few hours. But if you guys are interested, there are some really interesting resources here. There's a very good summary by Dan Liu from Microsoft, and I forgot where Matt Godbold is, but he's a very good engineer. He has a great understanding of Intel's architecture. But all standard processors, whether Intel or ARM, have instruction pipelining, branch prediction, cache prefetch, superscalar processing, SIMD or single instruction multiple data, out-of-order execution, etc. So you cannot really think linearly the way your program is actually written, even if it's an imperative program, because the processor just doesn't work that way. So I'm going to talk about some of those details in a moment. Yeah, so if you guys are interested in pipelining, this is really the best resource over here. One thing I definitely want to mention, because cache locality is pretty critical for this particular problem, is that it only takes us one cycle to access a register, about 3 cycles to access L1 cache, 14 cycles for L2 cache, and 240 cycles to access RAM. What does that tell us? That anytime we have a numerically heavy algorithm, the vast majority of the time is going to be spent, the processor is just going to spend waiting for data. It's not going to do any computation. It's bandwidth bound. It's not compute bound. So the processor is just sitting there. For those of you who remember electrical engineering, DRAM or the main RAM is actually relatively slow because even though the solution here is very simple, it's just a simple capacitor, you have to refresh the capacitors, you have to have analog to digital conversion to measure the voltage of the capacitor, etc. Whereas SRAM, which is how the cache is built, actually looks very complicated, but this is digital logic, so it's really fast. Unfortunately, this digital logic uses a lot of power, and on top of that, it takes up a lot of space, which is why we have kilobytes of cache, and we have, or megabytes at the most, and we have gigabytes in main RAM. So we have to live with these trade-offs given the technology that we have right now. And just to illustrate how important cache is, if you look at these 4 megabytes, which fit on a particular processor, this particular processor has 6 megabytes of, on this machine has 6 megabytes of L3, but let's say this particular processor in this demo had 4 megabytes. We see the differences between 5 and 10x for cache misses, because as soon as we reach the capacity of the cache, we're down here, right? So we definitely lose a lot of performance. And up here is registers, so definitely a big difference between registers and cache. But once we get down here, we're already out of the cache, and so the processor is mainly waiting for data. However, as you can see, random access is still half as fast as sequential access, which means that the CPU is still doing a good job at least prefetching the data. And this is actually another point that's important. So how can we speed up that stupid triple loop? Well, first of all, if we just reorder the loops, so this code, these 3 lines are identical, but we just reordered the nesting of the loops. So now we have K and J, not J and K. This means that we're first going over the rows of A, which is where we would get cache misses because C is a row major programming language, unlike Fortran, which is column major. And so accessing an individual row is much faster because you're utilizing the cache. So this index moves slowly, which is good. But then we also want to move across the, we want to fix the rows of B of the second matrix, and we want to go across the rows of the B matrix. So that way both matrix A access and matrix B access is by row, and that actually allows us to have more cache locality for both matrices. And guess what? We suddenly went from 1200 milliseconds to 167. That's a 6x speed up, right? That's becoming reasonable. That's still bad, but it's already, you know, only half as slow, half as fast as the NumPy implementation, but it's not, you know, it's not terrible anymore. That also tells you that GCC is a pretty stupid compiler, because the fact that you had to reorder the loops yourself means that it didn't do a good job optimizing. And I'm going to show you that Intel's compiler, ICC, actually would have figured that out for you, so we wouldn't have to do that manual tweaking. The next step, which is pretty common both in GPU and in CPU computing, is tiling. You can say, OK, instead of taking one row of one matrix and one column of another matrix just to compute one element, we can split this computation into multiplying this row by this column to get this element for this part of the matrix, storing that result in a register, then doing this computation, this row times this column, and then adding that to the results stored in the register. And so we basically split that computation into subsections, and that allows for even better cache locality. And this is becoming really horrific, right? I'm not even talking about like Haskell versus C++. I'm talking like even for you know, for C programming that is becoming really messy and nasty and pretty awful, but there are benefits. So at first, it would seem that there are no benefits relative to loop reordering, because the loop reorder and the tiling is about the same. If we actually did a micro benchmark and averaged across many iterations, it would probably be the same. And they're both much faster than the naive, but they're not really different from each other. However, this is because GCC does a poor job optimizing. If we switch to Intel's compiler, then suddenly we see, hey, Intel already optimized the naive implementation. We didn't have to reorder the loops. So same result with or without loop reordering, because the Intel compiler was smart. But our tiling solution actually gave us another 2x. So now you may have noticed the NumPy implementation was 74 milliseconds. We're at 56. We're faster than NumPy. So that's pretty cool. It's still slower than the GNU Octave solution because of Atlas, which is a self-tuning library that is more cache agnostic, or MKL in the case of MATLAB running on Intel CPUs. So you may get additional boost because Intel spent so much time tuning that library for different matrix sizes. So they actually have different subroutines for different matrix sizes. So that's just a crazy amount of work, but we are already getting reasonable here. Then there's this issue why people still use Fortran. I think that's kind of interesting, just as a side note. In Fortran, basically when you're dealing with pointers, Fortran assumes, hey user, you know what you're doing. You're not going to be accessing the same piece of memory from two pointers. And if you do, I'm not giving you any guarantees. That's why Fortran can hyper-optimize the code. Right? In C, because you can get race conditions and some non-deterministic result by accessing the same point in memory concurrently, or doing out-of-order execution on the same point of memory. In C, it's basically defensive, and it always synchronizes a block of code and says, hey, I'm preventing out-of-order execution. And that is causing a lot of slowdown, and this is why Fortran is faster. Now in C, there's this keyword restrict, and so you can theoretically get Fortran-like performance, but I still think that Fortran is actually faster. Obviously, anybody who grew up after the punch card era probably would not like to write Fortran anymore, but I guess it's good that some people did, so we can have fast linear algebra. And so the thing with pipelining is when your CPU is actually executing some piece of code, it's already decoding the next instruction, it's fetching the next instruction. So the pipeline allows the processor to always be executing something because it's already doing the decoding in the meantime. It's not waiting. The problem is if you have dependencies in your computation, you're going to get what's called a pipeline bubble. The pipeline is going to stall because it's going to say, OK, the next instruction depends on the result of the computation of this instruction. Therefore, I need to wait to see what the result of that instruction is. And this is very common. There's not much we can do about it, but sometimes we can, especially if our code is, has to be very performant. Once in a while, we can do some crazy stuff to optimize. So one example is loop unrolling. Here we have this accumulator, and if we have a for loop, because in the next step of the for loop, we actually depend on the result of the sum accumulator from the previous step, this actually stalls the pipeline. So that's very bad. That really reduces CPU performance. You can say, OK, what the heck can I do about this, right? This is as simple as it gets. Well, you can have two accumulators and update the loop counter by 2, and then you have 2 stalls, but the stalls are every other step, and then you actually have more opportunities for out-of-order execution and stuff like that. And then you just add them together. Hopefully a smart compiler would actually do it for you, but sometimes the compilers are not smart, as I showed with the GCC example. And in fact, if I pass this code through GCC, the assembly shows me that this loop exists. I compare, and then I jump to if not equal, and then I just move to values and add them. So obviously, it's purely sequential code. There's no optimization here. So GCC even screwed up that unrolled solution here, which is pretty awful. If I use Intel's compiler, it does vector operations, and it basically does kind of a reduction here. So it does element-wise addition here, and then it does a reduction of these additions from before. So it actually does parallelization of about 4x, and that has major performance implications. So if you're doing C programming on the Intel architecture, really use that compiler if you can, because it makes a big difference. Of course, cache awareness and stuff like that doesn't change the complexity of the algorithm. And there are algorithms with better complexity. So we're talking about the cubic order. And there are algorithms like the Strasson's algorithm, which is order 2.5. The best version of that algorithm is 2.5. Or Coppersmith-Vinograd, which is 2.37, right? Much better complexity than cubic. However, the problem with these algorithms is, as you know, big O doesn't always matter, because with Coppersmith-Vinograd, you would have to have matrices that are of the size bigger than the RAM of even the biggest machines for that complexity to matter, because the constant factor in that algorithm is so big that the complexity improvement doesn't make any difference. And people do crazy stuff in these libraries oftentimes by basically having different function calls for different matrix sizes. So it's really kind of a black art, but I think the general idea of using caching better, for example, and pipelining are pretty applicable to other problems. So I think it's an interesting insight. And this particular book, the famous CLRS book, actually does cover some of these matrix algorithms. OK. And then if you're really hardcore, you can do intrinsics. So you can do essentially what looks like assembly in C. It's basically calling intrinsic vector operations for different architectures like AVX for Intel or Neon for ARM, but this is really unnecessary in my opinion. You can do just fine without this kind of junk, and then because this prevents your code from being portable, so you might as well have written assembly at this point. There is something though that is platform independent, which is fuse multiply add. When you're doing a dot product of two vectors, you have a step where you add the result of a multiplication. So you first multiply, then you add. And so you can fuse that in one operation. Most CPUs these days, both GPUs, NVIDIA's GPUs and Intel processors and ARM processors actually have the ability to do fuse multiply add in one operation. So that cuts the number of computations by 50%, which is great. The problem, though, is fuse multiply add is less accurate. So you have 0.1 times 10 minus 1, and that it gives you essentially 0 for this float. But if you do fuse multiply add, there's a bigger precision error. So if you have computations that require a lot of precision, this particular optimization is useful, which is basically we're adding this FMA argument to GCC, and that will work on ARM, Intel, CUDA if we're using the NVCC compiler for NVIDIA, etc. And most compiler manufacturers actually do say, hey, don't use the fast math option, because fast math will actually crash and burn if you're doing precise computations. But if you're OK with that, that's actually a great benefit. And another example from Intel, it does the a vectorized multiply add, so you don't have to vectorize yourself, which is great. OK, finally, GPUs. I think you're probably more interested in GPUs these days because of deep learning and stuff. What are GPUs in general? The general philosophy behind GPUs is that they're high throughput processors because you have hundreds or thousands of threads running in individual arithmetic logic units instead of, let's say 4 to 16 threads on a CPU. But because you can only fit so much logic into these chips, they have a much smaller control unit, so they cannot do things like out-of-order execution and pipelining and branch prediction and stuff like that. So they're very good for number crunching, but they're really terrible for arbitrary logic. But if you have a high throughput problem that can be high latency, then that definitely is great. And that is definitely the case with most numerical processing, right? So linear algebra, deep learning, digital signal processing, stuff like that. Also, because GPU computing is mostly for number crunching, GPU programming is actually lower level than traditional C programming even, because you have the ability to, for example, programmatically access the L1 cache. It's called shared memory in NVIDIA's terminology. But it's really on the same chip as L1, so you can programmatically decide what goes into L1, whereas on a CPU, it's a black box, right? So you have to play with things that I showed before, but you have no guarantee as to what the cache eviction policy is. But the flop benefit, right, the number of floating point operations is huge. So if you look at Intel here, it's basically an order of magnitude less than the latest single precision NVIDIA GPUs, and they're even faster ones these days. So clearly, for algorithms that train for weeks, such as AlexNet or something like that, doing that without a GPU these days would be just ludicrous, right? Training a convolutional neural net of that scale. So we do benefit from the flops. But also the memory throughput is much better because the GPU is split into many streaming multiprocessors, which means that each of these multiprocessors has its own memory bus, and the memory throughput is also much better than in the case of the CPU. So yes, if you look at the sort of simplified representation, the GPU has plenty of cores, but the control unit almost doesn't exist. Whereas on the CPU, the control unit actually has more space than the cores, but but then the multi-threading is much more limited. So low latency and low throughput, high latency latency and high throughput. And this is pretty much how it looks internally. So each multiprocessor has a bunch of cores that execute separate threads, and each of these multiprocessors has a register file and a thread scheduler and stuff like that. But all of them have separate memory accesses, which is why the memory bandwidth is so high. And as I mentioned, in addition to global memory, which is traditional RAM, you can actually programmatically access not just, well, the registers are actually not programmatically accessible, but traditional, local variables in a function will do, and the compiler will optimize that, but you have access to programmatically controlled level 1 cache or shared memory. So the naive computation is very, very similar to the naive computation on the CPU. We take a thread which takes a whole row of A and the whole column of B and computes one element. But before we get to the computational examples, to the code, the general idea of using the GPU from your native application is that you first have to allocate memory on the GPU. You have to do a mem copy from the main RAM to the GPU RAM. Then you have to launch your kernel, which is your actual CUDA function that does the math. And then you have to copy the data back. So your application better be compute heavy, because the cost of going over PCI Express to ship the data to the GPU and from the GPU is huge. So if your computation is small, then your GPU computation could actually be slower than the CPU. So your data set be it's best for it to be rather large. Or if you can do something like SGD, right? If you're doing some kind of stochastic gradient descent or any kind of iterative computation, and you can keep the data in memory on the GPU and not ship it back and forth, then you finally get some benefit from the GPU as well. So this is a very simple GPU kernel. We have to refer to an individual thread block and thread index, and we iterate over K, which is that inner dimension that's conformant between the two matrices, and we finally get the result in this accumulator. We ship it back to global memory on the GPU or the main RAM. Unfortunately, it sucks. It's really slow. This is 280 milliseconds, which is better than the 1200 we had for the naive CPU implementation, but a reasonably optimized CPU implementation, even by me, was like 50 milliseconds, and the MKL implementation was 20 milliseconds. So what the heck is happening? This is pretty bad. GPUs are supposed to be magical, right? So we have to resort to blocking, just like we blocked, or tiling. Just like we did tiling on the CPU, we're going to do tiling on the GPU. But right now, because we actually have control over the level 1 cache or shared memory on the GPU, we can actually push the data into shared memory ourselves, and then it's going to be resident there until we release it or until the kernel goes out of scope. And so because of that, once we do this direct copy, all the subsequent computations are going to be based on shared memory, which is much faster than the main memory on the GPU. And so we do the same tiling as we did before. Now, that is unfortunately getting really nasty, because now we have to allocate shared memory, which is the level 1 cache type of memory. We have to push the data into this cache ourselves. Then we have to sync the threads across the block. Then we have to finally do this computation for the accumulator. And then we have to sync the threads again so that this doesn't go out of scope. And the reason we have to sync here is because we're doing tiling. So this memory will go out of scope after this loop. And so we basically have to sync before we go to the next step. That's already quite messy, right? GPU programming is really low level. If you thought C is low level, then this is lower level. This is like almost assembly, because you have to think about the hardware a lot. But we're getting better. So 193 milliseconds. Then there's this notion of aligned and coalesced memory on the GPU. Aligned memory means you are accessing memory based on your thread index. If you're accessing the memory not based on your thread index, or a multiple 128-byte multiple of the memory address, then you'll require more memory transactions. And normally GPUs ship 128 bytes at once, so a lot of data is shipped. And if you have multiple transactions, you're actually going to lose the whole performance benefit of the GPU. Coalesced means just accessing contiguous pieces of memory. So if you have several threads together, they should be accessing contiguous pieces of memory. So this is aligned and coalesced because it's on that 128-byte border. The consecutive threads are accessing consecutive pieces of memory. This is not consecutive, but these threads are still accessing this contiguous piece of memory. So that still is coalesced and aligned. This is misaligned because we're passing that 128-byte border, but the memory addresses being accessed are coalesced. So old GPUs had bad performance with misalignment, but new GPUs are actually stable. They don't care about alignment as much. So that's good. We don't have to worry about that crap, because how will we remember the memory address, you know? On the other hand, uncoalesced access, meaning accessing random pieces of memory and not accessing contiguous pieces of memory, means that there will be a lot of 128-byte transactions, and that would basically eradicate the whole benefit of using the GPU. So here's 100 gigabytes a second, and you get to maybe 10 gigabytes a second if you're doing striding. And what happens if you're taking the second matrix, the second operand in a matrix multiplication, and going down the column? Well, you're striding because the C memory, the memory model represented in a programming language like C is row major. So every time you're going down the column, you have a stride of the size of the row. So basically, this is pretty bad, and we'll need to figure out how to improve that. So now with coalescing, I'm not going to go through the details because there's just no time. We will get another benefit. So we went from 280 to 190 to 150 milliseconds, so that's better. Now there's this thing with bank conflict. So you can programmatically access the level 1 cache or shared memory in this case. And if each thread is accessing an individual address in a different memory bank, then this access is completely concurrent. However, if several threads are accessing several addresses in a given memory bank, then those accesses will be serialized because there's just one piece of, there are just 2 wires going right into that memory bank. But if different threads access different memory banks, so you can flip the memory access to this level 1 cache or shared memory, then you will get a huge benefit from that. So this is definitely several threads accessing one bank. You'll have 8-wise bank conflict, so you'll have 8 serialized operations. This is completely concurrent instead. So it's getting nastier and nastier because we have to think about the hardware a lot again. But we're now down to 100 milliseconds from 280, right? So we keep improving. Now, this is actually kind of a linear algebra trick. So finally, we're not thinking about the hardware, we're thinking about the math a little bit. That's more interesting. So what can we do? If we're doing a matrix multiplication, normally we just do this inner product, right? But what if we did an outer product of individual rows and columns? So here's an example. Here we have a 3x3 matrix and a 3x5 matrix, so the result is obviously going to be 3x5. But instead of doing an inner product, what we can do is we can take the first column of x and the first row of y and get a 3x5 already, then get the second column of x and the second row of y, get the 3x5, and do the same thing for the third row and the third column, and then add them element-wise. And as you can see, we get the same result from the inner and the outer. And why is that important? Because on the GPU, if you have 2 operands that are accessing shared memory, that access will be serialized. You cannot have 2 operands that access shared memory at once. So what we would rather do is put some stuff in the registers and only have 1 operand coming from shared memory. And so we can basically, each thread can access one element of each row of B. And the entire tile of A can be in shared memory. And we do as many iterations for each thread as there are rows of B. That way, we just store one element in one register for B. We just operate in a loop. And basically, B is in a register. One column of C is in the register per thread, and A is in shared memory. OK, this is horrible, right? Because in addition to all this thought process, I actually realized that I had to unroll this loop because I have another loop here. And even with C++ pragmas and stuff, it's not going to do a very good job. So maybe some loop unrolling was necessary here. But if you already know the loop size, then maybe that's OK. OK, so we're at 55 milliseconds. We're at the CPU speed, at least, at a reasonably optimized CPU kernel. If we just do kernel-only timing, so if you discount the whole shipping over PCI Express, it's 46 milliseconds. And so we went from 280 to 48. That's already a big improvement. But if you're into that kind of low-level thinking, then there are professional expert matrix multiplications for the Fermi, Kepler, and Maxwell architectures that have been implemented by experts. And they get into many more details about this kind of stuff. Now, if we use CUBLAS, which is NVIDIA's BLAS implementation, then we actually get down to 11 milliseconds. So I already optimized by 5x, and they optimized by another 5x. And so 11 is already better than the 20 milliseconds or so on using the Intel library on this machine. So this GPU is really tiny on this laptop, but it already does operate twice as fast as the CPU. OK, and just the last thing, if I use the Titan X, which is the top of the line GPU, then I would have gone down to 1 millisecond. So this is kind of an overview how we went from 1200 milliseconds on the CPU with a very naive implementation to 1 millisecond on the GPU with a very performant implementation on a big GPU. A difference of 1000x is huge if you're doing deep learning, right? When your algorithms run for days or weeks. So yeah, this is the overview of the timings. And I hope we have a little bit of time for questions. Yep?
Did you see that Google's going to make their new ASIC?
Yes, I heard about the ASIC. They call it TPU, Tensor Processing Unit. I was really excited when I saw that yesterday, but then I actually thought, OK, I think this is more marketing than reality. And I'll tell you why. One example. Here, you saw 3 orders of magnitude of improvement. They only said that the difference between the top-of-the-line GPU and TPU is 1 order of magnitude. Secondly, NVIDIA actually demonstrated at GTC in April that there's a ton of opportunity for improvement on the GPU itself, because, for example, between CUDA 7.5 and CUDA 8, using cuDNN, their deep neural network library, they got a 6x speed up just by changing the software on the same GPUs for recurrent neural networks. And considering how hard recurrent neural networks are to improve performance for because of the sequential nature, it just shows that improving software is still the way to go relatively inexpensively. The next thing is the Maxwell architecture gets an enormous boost. Sorry, not Maxwell. The Pascal architecture gets an enormous boost in performance. And the final thing is Microsoft actually demonstrated their FPGA implementation. So FPGA is programmable hardware. And FPGAs are normally much slower than ASICs or application-specific integrated circuits. And Microsoft's FPGA implementation was about as much of an improvement as Google's hardware, but you can reprogram the FPGA. So you can change the algorithm, and I think that's more flexible. And even Intel has FPGAs built into their Xeon processors now, so yeah? Yeah, sure.
Thank you. Let's say things.
Thank you.